I will turn the event over to Amnon Shashua, the professor of computer science, the Sachs professor of computer science at Hebrew University, whom I've had the pleasure of knowing for many years, and I can't tell you, Amnon, how much I appreciate the fact that you've come. Amnon has told me many times anything that he can do to support my efforts and also the forward movement of the American Friends of the Hebrew University. He never says no, and so I thank you so much, Amnon, for coming. And I think you've all read, so I'm not going to take the time. You've all read the biographical description, and a lot of the work that Amnon's done we're going to get into here in the question and answer session and that follows. So, thank you very much.
Thank you. Thank you. Well, thank you all for coming. I'm really honored that you came to hear what I have to say. So I'll try to make it entertaining. So I work in machine learning, computer vision. Today it's all called artificial intelligence, but it's really the kind of science that tries to mimic the way humans think. So try to mimic the way humans perceive the world, try to mimic the way humans make decisions, and there are many domains in which this becomes useful, and one of those domains is cars. If we can have cars drive by themselves without having a human driver behind the steering wheel, we will achieve two big things. First, a true vision zero in terms of accidents, because there's no more drunk driving, no more drunk driving, no more people who are not concentrated on driving, because machines will be continuously vigilant. Second thing that we could achieve is much higher utilization. Cars today are underutilized. A car, the statistics of utilization is a car is 96% of the time idle, staying in a parking lot. But if we have cars without a human driver behind them, those cars could be active 24/7, creating mobility on demand at much lower costs than today, because today the driver is about 50% of the cost. And that could change the world of transportation. It could change the world of car ownership, right? Because today, a household owns several cars. Imagine a world in which the car can drive on its own. I can take my car to work, whether the car is taking me or I drive the car, doesn't really matter. I get to work, the car goes back empty on its own to my home, and then takes other members of the household to wherever they need to go, and in the evening it will come back and take me. So you can imagine, the transformation in terms of car ownership and mobility. Okay, and
you have a full house.
Yeah. And mobility if we could have self-driving cars. But in order to make self-driving cars, you need to solve big and difficult problems. And those problems are related to artificial intelligence. And why they are related to artificial intelligence? Because in order to drive autonomously, you need to solve two big problems. The first one, you need to perceive the world at levels very, very close to human levels of perception. So perceive the world is, you have sensors, let's assume that those sensors are cameras, that you have information from the cameras going into high performance computing, into computer chips, and they need to process that information and create a model of the world outside us. So the model of the world is, where are the road users, vehicles, pedestrians, where are the traffic signs, traffic lights, what are the drivable paths, in order for us to understand how to drive forward. So perception is difficult. It has been an area, it still is an area of research that began about 50 years ago, and success was very, very slow until about 5 years ago. 5 years ago there was a big jump in ability to do pattern recognition. If you look today, for example, at take your albums and Google Photos or Apple or Facebook and do face recognition. The face recognition of today is very, very impressive compared to where it was 5 or 10 years ago. This is a testament to the rapid progress in machine learning and in pattern recognition that has been happening in the entire industry. So perception is a difficult problem, and for humans it's easy, because one thing that many people don't know, 50% of our cortex is focused on visual processing. Because it's such a difficult problem, most of our brain is focused on processing visual information. So it is a very, very difficult problem. So the first problem we need to solve is perception. The second problem we need to solve is making decisions. So merging into traffic. And we know it is difficult because we take driving lessons. Right? So when we take driving lessons, it's not for the reason that we need to train our sensors, to train our sensing. We know how vehicles look like, how pedestrians look like. We can easily understand what is the drivable path. We take driving lessons because we need to negotiate. We need to negotiate with other drivers, especially, the spectrum of behaviors is very, very wide, from aggressive driving to cautious driving, and we need to merge into traffic in a smooth and safe manner, and we need driving lessons, and then later, after we get our license, to practice, to do that well. So a computer needs to do this as well. So the decision-making, negotiation is an area of artificial intelligence which today is used in gameplay. So when you play chess, when the computer plays chess or computer plays Go, it is using this part of machine learning which is engaged in game playing. So you need that part of machine learning for self-driving cars if you want the car to merge into traffic. So those are two very, very big problems of artificial intelligence that you need to solve. And then comes two additional problems that are less obvious. So the two problems that I said, to those who are in the field, is kind of obvious. The two other problems that are less obvious, I'll start with, I'll rank them. The first one is about maps. So machines need a very, very detailed map in order to drive autonomously. Humans do not. Right? We need a navigation map if we want to get someplace. Right? To know how to get to a certain address, I need a navigation map. Whether it's a paper map or Google map, we need a map. But to drive, we don't need a map. So you can go to a new city, rent a car, and simply drive. Right? Machines need a very, very detailed map in order to drive. And the reason that you need a very detailed map is because of redundancy. Whatever the machine does, it has to do it in multiple ways. So for example, if there is a car in front, you need to be able to detect that car from multiple sensors, from a camera, from a radar, maybe from a laser scanner, in order to create the level of robustness that you need in order to make sure that the performance is going to be perfect. Now, when it comes to sensing the lanes, there is only one sensor that can do that, and that's the camera. The camera is a sensor that can sense both texture and shape. Whether radars and laser scanners, they can sense only shape. They cannot sense texture. So the redundancy for the camera will be the map. If you have a detailed map means that you have all the information, all the stationary information about the lanes, their semantic meaning, the traffic lights, traffic signs, all of that is in the map. If you locate yourself in the map at an accuracy of centimeters and project that data into your space, then you have redundancy to what the camera senses. And this gives you the robustness in order not to make mistakes. Now, why I'm mentioning that? Because building these maps is very, very difficult. And if you want to build a self-driving car industry, you must be cost conscious. Right? Today, building these maps will be millions of dollars for a small 10 miles per 10 miles area. And the problem is also updating the maps. If you need a map in order to drive, that map should always be true. It should reflect reality, and reality changes. There's construction going on, things change in the world, and they change quite frequently. It's not they change once a year. The frequency of changes could be days. So you need somehow to update this map continuously, but in order to build this map, it took millions of dollars for a very small area. How do you go and update these maps? So it's a big logistical problem that there are ways to solve it using sophisticated technology. I'll mention that later. And then the second, even lesser obvious problem, and this is even professionals kind of grapple with, and many do not understand the depth of this problem, it's about safety. Now, what does it mean about safety? So, of course, the first sentence that you have in mind, yes, we're going to build safe self-driving cars. Who's going to build a non-safe self-driving car, right? But when you start thinking about it, how do you go and define safety? Right? Because if you want to be perfectly safe, don't drive, right? Or stay in the parking lot, right? Once you are driving, you are taking risks, especially if you are driving in an agile manner, right? You want to change lane, and the road is congested, so you are interfering with the other road users in order to change lane. What does it mean to interfere with the other road users? You are raising the chance that there's going to be an accident. So you need to define what safety is. And the problem here is that there is an asymmetry between how society treats human-related fatalities and how it will treat computer-related fatalities. We are very, very sensitive to machines killing people, and we are less sensitive for people killing people. Right? So if you think about the number of fatalities in the US, there are about 40,000 accident-related fatalities a year. And then let's do this kind of thought game. If we replace all humans, all drivers with computers, and those computers will still kill 40,000 people a year, society will not accept it. But even if we say, you know what, we'll do better. We'll kill only 10,000 people a year. Right? Definitely, from a rational thinking, we're doing something good. Society will not accept computers killing 10,000 people a year. Right? So we need to be orders of magnitude better in order for society to accept this. So we need to come with guarantees of how these machines are going to behave in the real world. And these guarantees is the problem. How do you go and define it? So when you start thinking about the rules of driving, many of the rules of driving are well defined, but then you come up to some rules that are completely ill-defined. One of the major ones is called duty of care. So duty of care says that in any business that could harm people, you need to exercise care. Now, it's not only in driving, any business that could harm people. Now, what does it mean to exercise care is left for interpretation. It's societal norms, it is legal precedences of previous accidents, how the judge and the jury decided who is to blame for the accident, and that creates precedences of who was careful and who was not careful. But for machines, you cannot leave it open. Right? You have to go and define it. And there it becomes tricky, because it's not just a philosophical exercise. You need to optimize. I'll show you also pictures and movies later, but I'm just setting the stage. So you need to optimize 3 dimensions. The first dimension that you need to optimize is that whatever interpretation you have of the duty of care needs to be sound. Sound meaning that should comply with the way humans perceive or interpret the duty of care. You cannot come up with an interpretation that's completely bizarre. That is, it's not the way humans understand what being careful means. The second axis that you need to optimize is usefulness, right? Because you can have a definition of cautiousness that's completely not useful. So I'll give you an example of something that sounds very rational, sounds very reasonable, but it's useless. Let's assume that I'll make a definition of being careful such that when I change lane, all other road users should continue the same speed. So I'm basically not interfering with the motion of other road users. So let's assume that the road users are vehicles. I want to change lane, so I can change lane only if other vehicles will not change their speed. Sounds very, very careful. Right? I'm moving without interfering with other people's motion. That sounds an ideal definition of being careful. But in most places in the world, you cannot change lane in that way, because if the traffic is congested, you cannot wait until the huge gap will be between 2 vehicles so that you can change lane without other road users slowing down. So you need to negotiate with other road users, force them to slow down, otherwise you'll not be able to change lane. So here is a definition, a bad definition of being cautious. It's good from a philosophical point of view, but it's bad from a usefulness, a utility point of view. So this is another axis that you need to optimize. You need to be sound and useful at the same time. So you need to allow for agility. Then comes the third axis, and that's very, very non-obvious. So these 2 axes, you can philosophize. You don't need to be a mathematician in order to. The third axis requires math. You need to come up with an interpretation that can be implemented in a machine, that can be verified in a machine. In other words, you need to prove that there are no butterfly effects. So butterfly effects meaning I'm doing an innocent action now, then there's going to be a chain of action, reaction, action, reaction. Accident is going to happen, and that accident is traced to the innocent action I made right now. So it means that I can never make an action and then verify that this action is safe, because later in the future, an accident could be created. So in order to verify, I'll need to roll out all possible futures, and that's, from a complexity point of view, not possible to do. So I need to come up with an interpretation, sound and useful, but it has to satisfy the inductive principle. Inductive principle meaning that if I make an action right now and I prove that this action is safe, it's also going to be safe into the future. An accident is never going to happen because of this action that I made right now. So I'll give you an example of an interpretation that sounds reasonable but does not satisfy the induction principle. Let's assume that my definition of cautiousness would be that if I'm tailgated by another vehicle from behind, it's too close to me, I'll simply accelerate a bit to increase the gap. We normally do this, right? You see someone from behind and you think he's too close to you, and the road is free, you accelerate. You can prove that if you do this, you can never have the inductive principle. You'll have to roll out all possible futures in order to prove that by accelerating, you're not going to create an accident. So you'll have an interpretation that may be sound and useful, but not implementable in a machine. And this is where the mathematics comes in. So you have to optimize three axes: sound, usefulness, and efficiently verifiable by a machine. So when you start building an autonomous car, there are certain problems that you need to solve that are completely not obvious. The first two problems, perception is obvious. It's difficult, but obvious. Making decisions is difficult, but obvious. Obvious that you need to solve this problem. The other two problems, mapping and all this issue about safety, how do you go and define it, how do you guarantee it, is completely not obvious. And this is why it is so exciting to be engaged in this kind of domain, because it becomes an ideal platform for developing artificial intelligence. A self-driving car is the only problem in which all aspects of artificial intelligence are represented. Pattern recognition, perception is represented. Decision-making, game playing, all the technology for game playing exists in self-driving car. For example, I'm sure that all of you heard, or most of you heard about, the big success of Google's DeepMind in playing Go, the game of Go. Right? So chess used to be a big challenge 20 years ago, until IBM Deep Blue's program was able to beat chess masters in playing chess. Go is a Chinese game which is much more difficult than chess. And about a year ago, Google, through their purchase of a small company, a British company called DeepMind, well, today it's not that small, it has about 1,000 people, they created a program that could beat masters of the game Go. And that's considered a very, very big challenge, and they succeeded in this challenge. The technology for playing Go is the same technology we use in self-driving cars for making decisions. So you have here a platform in which all the major pillars of building AI is represented. This is why this domain is so exciting to Silicon Valley companies. It's not only the potential of building a new business, self-driving cars, mobility as a service, changing ownership of cars. You have passengers in the cars, then you can start transmitting content and customer experiences. There's a big business around it, but that's not the full story. There is also the potential of developing AI that can later be useful to other domains, to other verticals, not only to automotive. This is why Google is playing there in this field. This is why Apple, even though Apple is very secretive, nobody knows what they're exactly doing, but we all know that they are developing self-driving cars, or trying to do that. It's not only because of the business. It is because the technology that you need to develop for self-driving cars is technology that you can later transform and reuse or pivot into many other domains that require AI. In a self-driving car, we have about 12 cameras around the car, giving us 360-degree sensing. And then we have radars and laser scanners to create redundancy. for increase of robustness. But let's focus on only on the cameras, because the cameras are sufficient to provide an end-to-end solution for self-driving cars. So this is one of the cameras, a front-facing camera. So while the video is moving, you'll see an overlay of what the computer does by interpreting the visual field. So it will put bounding boxes, 3D bounding boxes on vehicles, on pedestrians. This red line is going to be the free space. Where is the area in which the car can maneuver? So the free space stops at stationary objects, could be a pavement, stops at other vehicles. Basically, wherever you cannot move is outside of this free space. Let's have this run. So you see that the 3D bounding boxes. You see this green line. This is the lanes. So the red line is the free space. The green line is the lane. You see bounding boxes on traffic signs. We just passed through them. There was a bounding box on a pedestrian. So this is part of what the computer does in perceiving the world. It takes an image, which is part of the video. It takes an image. What the image contains only pixels. So it is an array, when each element of the array is simply a number between, say, 0 and 255. It's an 8-bit number. It gives us a gray value. So these are pixels. It needs to take these pixels and transform them into higher level percepts. Transform them knowing that these collection of pixels is a car. These collection of pixels is a pedestrian. These collection of pixels is a lane marking. This is a fragmented lane marking. This is a solid lane marking. This is a road edge. This is a curb. This is a traffic sign. What exactly that traffic sign says is also part of perception. This is a traffic light. What is the state of the traffic light? What is the relevancy of the traffic light? Is this traffic light relevant for taking a left turn? This traffic light relevant for going straight? Then the drivable path. Is this path and the path beside it are going to merge? Yes or no? Because there are pavement markings that will tell us whether they're going to merge or not. We saw the pavement marking, say, 20, 30 meters away. This is all part of perception. And what's difficult about it is that the input is only a bunch of pixels. Right? When you think about it, when we look at the world, we don't see pixels. Right? If you have never seen a camera in your life, you wouldn't know what a pixel is, right? But this is the input to the computer, just a collection of pixels, and you need to transform it into a higher level person. So this is part of perception. In terms of mapping, so I mentioned that mapping is a difficult problem. So how do we go about this? The way we go about it is we use a crowdsourcing. So what's the idea? So we all know about crowdsourcing, we all know about Waze and all these navigation programs. I'm talking about a different kind of crowdsourcing. So let's digress a bit. And I've been talking about autonomous cars, but there is a much bigger industry, and that's called driving assist. This is where Mobileye is making its bread and butter. This is where all the money comes. Self-driving cars is way into the future. There's no money in self-driving cars today. All the revenue is coming from driving assist. Now, what is driving assist? The front-facing camera perceives the world, just like in this video that you have seen, identifies the cars and pedestrians and other relevant information, and protects the car against collisions. So it will know that you're going to collide into another vehicle, and it will start actuating at first warning and then braking such that the accident will be avoided or mitigated, depends on the speed. Now, this kind of technology is today regulated. It means regulatory bodies are putting down incentives to car makers to make sure that every car comes with this kind of technology through star ratings and through mandates. It started in the US, then Europe led, now back to the US. Basically every new car today comes with a driving assist technology. Mostly it's camera based, with a driving assist technology that is basically standard in the car. You are not even aware it exists unless you're about to collide, and then you feel that automatically the brakes have activated. So Mobileye is the dominant supplier of this technology, about 90% of the market. So the purchase of $15 billion was not just based on pipe dreams of how the future would look like. It was based on the fact that the company is the dominant player in driving assist. Now, why I'm telling you all of that? Because the idea of the maps is to leverage this dominant position. If almost every new car comes with a front-facing camera, to give you numbers, 2018, Mobileye shipped about 13 million microprocessors, and it's a microprocessor per car. So 13 million cars on the road in 2018 have a Mobileye technology. So if every new car has a front-facing camera, let's add to that camera communication capabilities. Let's have additional software contained in this processing chip that will do two things. One is identify landmarks. So landmarks would be traffic signs, traffic lights, pavement markings, poles, reflectors, anything that is stationary in the world. Identify those landmarks, and then collect the lane information, packet it into something which is relatively lean, about 10 kilobytes per kilometer. So 10 kilobytes per kilometer means that if you drive a year, 20,000 miles, it's about 200 megabytes of data. Sending 200 megabytes of data to the cloud is about $1 today. So the cost is reasonable, $1 per year per car. Send this data to the cloud, and in the cloud you automatically piece all of this together and create a very, very detailed map. So let me show you an example of this. So what you're going to see here is the following. On the left-hand side, you're going to see a video. The video has two pieces of information. It has these yellow rectangle bounding boxes. These are the landmarks that the system detects. It uses the landmarks to position the vehicle inside the map at an accuracy of few centimeters. Right. Very, very, very high accuracy. The lines that you see is map data projected onto the image. And those lines sit on lanes and road edges on the road. And if the map is not accurate, you'll see an offset between the line and the true lane mark. But it's very accurate. The accuracy is few centimeters. So you'll basically see those lines aligned perfectly on the lane marks. But it's only a testament to the accuracy of the map and accuracy of localization. On the right-hand side, it's the same video. You're simply seeing a top view on Google Earth, where all these circles are the landmarks, and the lines are the map data. Okay? So you can see how those lines sit exactly on the lane marks. The purple are the lane marks, and the one in between, this kind of greenish line, is the center of the lane. And all the yellow bounding boxes are landmarks being used to localize the vehicle inside the map. And all of this was created through a crowdsourcing. And the crowdsourcing started this year. So BMW, it's about 1 million cars sending data all the time. Volkswagen is now launching. Nissan is now launching. So by 2020, almost all car that has a Mobileye chip will start sending data, and those maps will be built automatically and then updated in real time automatically. So this is a way to solve this mapping issue through technology. Here is, I think that this is an interesting video to show. So I told you that with the safety thing, you need to optimize agility. So to give you an idea what it means to be agile, I took a drone about my road to work. Now, Israeli driving, I would compare it to France, Italy, Boston. So imagine these kinds of driving. So it's not as far out as India or certain Asian countries, but it's intense. It is intense, right? Especially if you come from California, you go to Israel, you could be shocked in terms of the driving culture. So let's have a look at how it looks like, and we need computers to be able to handle these kinds of situations. So this car is now merging in. You're going to see the car that is being circled is trying to merge to the left, but will not succeed. At some point, we are fast forwarding it, and see this poor guy. Nobody lets him get in.
That's just mean.
So imagine a machine having to handle this, or this truck, this long vehicle needs to merge to the left. And again, we're going to fast forward, and it takes ages until it succeeds, because nobody is relenting, right? So this is the kind of agility that you need if you want to drive in a culture of driving like in Israel. And if you cannot, then it means that your market is very, very reduced. I mean, if you can drive only in certain areas of California or certain nice places in Phoenix, Arizona, then your market is very, very small. If you want a big market, you need to be able to drive in these kinds of culture. This is a test car that we have. The test car has 12 cameras around the car, and you'll see how those cameras are located. There are 3 in front with 3 different fields of view. You're going to see it in a moment. So it's about 150 degree, 50, and 28. So it gives you wide field of view and long range by processing those 3 cameras. And then you have corner cameras, 100 degrees field of view, to get the corner, and then also corner rear cameras. And after that, you have parking cameras that give you the short range. So 4 parking cameras on the mirrors, 1 on each side, and then the front and rear bumper. So altogether, it's 12 cameras. These 12 cameras, all the data is fed into our microprocessors. The same microprocessors that we designed for driving assist is being used for autonomous driving. And it gives you this kind of behavior. So what you're about to see here is how the machine handles aggressive driving. Right? So it is to show the agility of the decision making, and it's all under this interpretation of duty of care, this mathematical model that will guarantee that you never cause an accident. So what you're going to see, the videos are coming from the cameras. This you can ignore. Let's focus on the center, which is the top view. So the top view shows kind of the integration of all the sensing, of all the in understanding the environment. And the color codes as follows. If an object is white, it means that this object is not interesting. It doesn't affect the control of the vehicle. If the object is magenta, this one here, it means that that object is affecting our control, that we need to slow down in order to keep a safe distance. The other interesting color codes is the red and the green. So in order to change lane, you need to find a gap between a vehicle that you gave way and a vehicle that you are taking way. So if you are giving way to a vehicle, it's color-coded in red. And if you are taking way of a vehicle, it's color-coded in green. So in order to change lane, you need to change lane between red and green. Now the machine, the computer, makes the decision every fraction of a second. So it could make a decision that it wants to take way of a certain vehicle. It will start a maneuver to change lane by making the assumption that it's going to take way of a certain vehicle, but that vehicle doesn't allow it to take way, right? So it will start accelerating. So then the machine, you don't want to create an accident, right? So you understand that that vehicle is not going to give you to take way, so you relent. Now what do? If you return back, this is a non-human behavior. When we change lane, we don't do like this. Attempt, not succeed, go back. Attempt, not succeed, go back. What we do, we start our attempt, we let that vehicle, that aggressive vehicle, to overtake us, but we stay in the same position, so that the other vehicle would know our intent, would know that we're serious in changing lane. Because if we go back, we have to start all over again, and then we'll never complete the maneuver. Right? So this is the kind of behavior that we expect humans to do. Gradually make your signaling, stay, hold the line, so to speak, and then at some point, the vehicle that you decided that you take way will have no other recourse but to let you take way, and then you complete. So what you're going to see when I run this video, this red and green are going to change colors all the time, because it's trying to change. That vehicle does not allow it to. So it will change the color into red. So let's have a look at this. And this is congested traffic, very congested traffic. So you can see how the blue car decided to take way of this green car. So the green car now all of a sudden turned to red. Why? Because it's not allowing it. It's accelerating. Now it's making it, but the blue car is still holding its place. And now it's exceeded in changing lane. And now it will do it again. Again, it was green, and now it's exceeded. Let's have, in very, very congested traffic, let's have a look here. It's going now, the blue car is going to change lane to the right, in between the red and the green car. And then it will do something very human-like, and it will accelerate. It will accelerate towards the red, and then change lane. This is something that we humans do. In order to change lane, sometimes we accelerate in order to fit into the gap. Now, the interesting thing about all of this is that these behaviors were learned through simulations. So it's not that it was hard-coded into the program, this is how you need to behave. So how did the machine learning work? Machine learning work is we build a simulator that creates all sorts of behaviors, even non-human behaviors, all sorts of behaviors. And the robotic agent needs to maintain safety while executing the task. Executing the task is change lane. And through multiple runs, we're talking about billions of runs of the simulator, the habits that are being learned are the habits that you see here that are very human-like habits. Yes?
How much easier is it all the cars are autonomous driving?
Of course it will be easy. The problem is that in order to reach a stage in which all cars are autonomous, you need to pass through this void, this valley of death, in which it's a mixed situation, that you are driving amongst humans. Because if you isolate an area and you say that area is only autonomous cars, no city, especially congested cities, are going to sideline major arteries and say these are only for autonomous cars. So you need to be able to solve the more difficult problem, is how do you drive amongst humans? Once all cars are autonomous, and that could happen, I don't know, 50 years from now. Once all cars are autonomous, then things become much, much simpler. You don't need even traffic lights. But if all cars are autonomous, they can communicate with each other. You know the position of all other cars. You can maneuver moving through junctions in a way that looks science fiction, right? Without any traffic lights. But to reach that stage, you need to pass through this stage in which there's a small number of autonomous cars, large number of humans with their culture of driving, and you need to be able to merge and behave in a natural way, in a human-like way. And this is a very, very difficult problem to solve. Let me show you the last one. Here's a motorcycle. This green is a motorcycle. The blue vehicle is trying to take way, but the motorcyclist is moving fast. Then change into red, meaning that it's giving way to that motorcycle. Okay. So I think I'll stop here. I think I'll stop here to leave ample time for questions, because normally this domain is intriguing and interesting, and people have all sorts of ideas. Go ahead. So we see this progressing in generations. Generation 1, starting in 2021, you handle only good weather conditions. What does that mean? Say you are now building a mobility as a service. Say you are Uber or Lyft. So you have a mixed fleet. You have a fleet of autonomous cars, and you have also human-driven cars. Now, when a customer orders a vehicle, it will receive either an autonomous car coming to pick him up, or a human-driven car, and that's depending on the weather. Now, in order to make this useful, you start in areas that have good weather. This is why all the tests are being done in California, in Phoenix, Arizona, in Los Angeles. It's not a coincidence that all these places have good weather conditions. Right? There's no snow. Right? Excuse me?
And grid?
It's not a matter of grid. It's a matter of simplifying the weather issue. Now, in order to handle bad weather, you need better sensors than we have today. So the kinds of sensors that we have today are cameras. Cameras are improving in the resolution, improving in the light sensitivity. There are radars. Radars have a long way to go to become really useful. Today, radars, the resolution is very, very poor. Within 5 years from today, we'll have what is called imaging radars, where the resolution of the radar is sub degree. Today, resolution of radars could be 10 degrees. So a radar will give you an image just like a camera gives you an image. And radars are weather perfect, they're not sensitive to weather conditions. Laser scanners are less sensitive to weather than cameras. Laser scanners today are very, very expensive, but in 5 years, there's a very, very good chance that new technologies of laser will bring the cost down considerably, and then you can have also lasers to handle weather conditions. So, and this is considered generation 2. Start 2021 with machines that could drive in good weather conditions. There's a business case for them, as I said, in this mixed fleet. And then generation 2, which would come 2, 3, 4 years later, would have better sensors that could handle also bad weather conditions. Yep.
How far away are we from over-the-road trucking depot to depot?
In trucks?
Over-the-road trucking depot to depot versus inner city?
Well, there are a number of use cases for autonomous driving. One, it's city driving, mobility on demand inside an urban setting. Another one is highway driving, going from... Now, highways, they have difficult challenges. One of the difficult challenges with highways, so it looks from a layman perspective that city driving would be the most difficult. Because as the kind of example that I've shown here, you need to merge into traffic and dense traffic and so forth. The problem with highways is range. Say, for example, somebody threw a tire on the road, 20 centimeter height object, that if you go over it, you can flip. Now, detecting a tire from, say, 150 meters away is very, very tricky. It's very, very difficult. And doing it in a robust manner is also very, very difficult. So it means that if you want to drive on a highway completely autonomously at, say, 130 kilometers per hour, it is very, very challenging. It's more challenging than driving autonomously inside the city. So it's a different kind of challenge. It's sensor range challenge that eventually will be solved by better sensors. But today is very, very challenging. This is why the focus really is on city. Yeah. And it's non-obvious because you think that highway is easier. It is easier in terms of merging into traffic. It is easier in terms of control and planning. It is easier in terms of perception of where other vehicles and pedestrians are located, or normally on highway there are no pedestrians. But hazards is a big issue. A tire on the road, a small object on the road, I'm not talking about a vehicle. Small object, 20 centimeters height. You need to be able to see it 150, 200 meters away in order to start maneuvering, either slowing down in a comfortable manner or maneuvering in a way that will allow you to avoid this hazard. So that will take more time. Yes?
How do you avoid hacking? How do you avoid hacking of the system?
Well, there's another domain that I did not talk about, and that's cybersecurity. And there are many companies whose focus is on building cyber defense for cars. Today, you can hack into a car through the FM radio. Cars are being connected, so you can hack through the connectivity. Now the GPRS or the LTE connectivity, you can hack through them. So it's a big issue, but there are many companies working on it. We are also working on creating a cyber defense at the chip level, at the platform level. It's an issue which is solvable, but it is an issue. Yep.
How do insurance companies foresee reacting to? Is it going to be?
So how do insurance company play a role? So let's take the driving assist, because driving assist has been existing for quite a while. And you see that the insurance companies are not the dominant player. They are hardly a player in driving assist. So there are organizations, insurance organizations like the IIHS organization. They issue reports, good reports, and so forth. But the dominant actors are the regulatory bodies, the NTSB, the NHTSA of the world, that create incentives and mandates that push car makers to make this technology a standard fit. Right? I believe the same thing is going to happen with autonomous cars, that regulatory bodies would coalesce around the idea of autonomous driving, about putting the right regulations for autonomous driving, because it solves critical issues. It solves the issue of fatalities. The cost of fatalities, the cost of accidents is huge to society. It's not only the loss of life, but also the huge expense, especially with non-fatal accidents. That solves a big issue. And second, smart cities. Cities can be planned in a much better way without all these huge parking lots that are wasting a lot of space if cars would be autonomous. So it's not the insurance companies that I believe would be a major player in this industry. It's still the regulatory bodies that will play a role, just like they do in driving assist. Yes?
You mentioned smart cities, and also was talking about the question of when all the cars are autonomous, and it seems like the end game of this is far different from the intermediate stages, and all the money that's being invested in this research and development and the very micro transitions from one thing to another, it seems like an answer to this would be a smart city, a city where a car company would invest in making the city or the town or the municipality fully autonomous, and proving, as a case study, proving the efficacy of a different kind of autonomous vehicle. Is there any talk about kind of jumping ahead of what you're incrementally developing and trying to develop the end state and seeing whether, from a cost perspective, it would be more efficient to simply jump to that?
Well, first, we're not developing something incremental. We're developing a fully autonomous car that can drive amongst humans. It will be simpler if it can drive only amongst autonomous cars, but we are solving the more difficult problem that can drive autonomously amongst humans.
But
so it's
some
not
of the problems
incremental.
you're solving are not problems that would exist if all the cars were communicating with each other.
That's true, but the point that I'm making is that you must solve these problems, otherwise you'll not reach to that stage. Let's take, for example, let's again take driving assist as an example, and let's take lane departure warning.
Where the off button is.
We need a highly technical man to
There you go. Give the man an autonomous car.
So,
Now give her an autonomous mode.
so let's take lane departure warning. So what does lane departure warning mean? Is that you have a sensor, the camera, detects the lanes, the position of the car relative to the lanes, and if you are veering out, you'll get a warning, either an audible warning or vibration of the steering wheel, so that if you are kind of sleepy, you'll wake up and go back to the center of the lane. You could have solved this problem without any sensors, just through infrastructure. Create magnets on the road, and with very, very simple technology, solve this problem without having sophisticated sensors and the camera with, very, very advanced, computer vision. The reason why this did not happen is that there is no money in infrastructure. Municipalities are stripped to the bone and do not have money to invest in these kinds of science projects. So if you want this to become reality, it is the technology providers need to build the technology and not rely on changes of infrastructure.
Or Jeff Bezos.
Yeah, but how many Jeff Bezos you have?
You only need one as a proof of concept.
So you prove concept, and then what?
Yeah.
And then what? Okay, so it remains a science project, right? If you want this to become an industry, you need to solve the hard problem. Even though 50 years from now, it will be redundant. You won't need to solve that hard problem. But if you want mobility as a service to be commercial without human drivers behind the steering wheel, you need to solve the hard problem, which is you need to drive amongst humans. If you don't solve that problem, go do something else. Right? It's not going to happen that all of a sudden, a big chunk of a city, of a lively city. I'm not talking about someplace in the suburbs that nobody lives there. No, a piece of Philadelphia, all of a sudden you'll keep it only for autonomous cars. No city will do that. Okay. So you need to solve the difficult problem. Yeah.
What is LiDAR?
Radar, a LiDAR or radar?
LIDAR?
So this is laser scanner device. So you have a laser emitting so there are two techniques, one being used and the other one still developed. You are emitting a burst of laser beam. That laser beam hits whatever obstacle, and then you get a reflection back, and you are measuring the time difference between when you emitted the burst of laser and when you receive back the photons of light coming back, and this time difference tells you the range to that particular obstacle. Today, these are rotating laser beams. So you have a laser beam rotating, and then you have a number of those in order to create vertical resolution. And these are very expensive. They could be tens of thousands of dollars, say 32 or 64 rays rotating. Future technologies is more solid state. Is using techniques which is frequency modulation. Rather than sending a burst of energy, you send a wave. This wave, you are changing the frequency in in a step manner. This wave hits the target, hits the obstacles, and then a wave comes back. And that wave is modulated. It's called chirps. It's like delta function. And the way it is modulated tells you something about the depth. And this doesn't require any moving parts. And this is something that you'll start seeing in 5 years from now.
Is that the new era of like a sonar? Is it the same concept?
Well, it's the same concept of emitting waves. So in sonar, it's sound waves. It's all a matter of what
So
frequency.
It's different waves.
So radar is radio frequency. LiDAR is coherent light. It's slightly above the visible spectrum. So the visible spectrum is 400 nanometers to about 800 nanometers. LiDARs work at 1300 nanometers. So we don't see it, but it's not that far away from the visible spectrum. Sonar is sound frequency. And I said before, and cameras visible spectrum, just like our eyes, 400 to 800. Then there is infrared, the IR, there's near IR, which is in the 1000 nanometers, so 1 micron. And then there's far IR, which is about 15 microns. So it's all about the wavelength. And the wavelength determines what technology you need to use. That's
So what's the social implications of this? Gotten rid of the cab drivers, gotten rid of the truck drivers. Where are they going?
So social implications, so not everything is worked out in terms of the social implications. Design of cities could change because you don't need so many parking lots. Ownership of cars could change because, as I mentioned before, a household doesn't need multiple cars. One car, it could be me and my neighbor will share a car, right? If this car is a much higher utility. Mobility as a service becomes much more economical because the statistics shows that the driver is 50% of the cost. So imagine Uber reducing the cost for 50%, all of a sudden mobility as a service becomes economical, right? It becomes something that you not only have revenue, but you have also profits. Today, Uber doesn't have profits, right? So mobility as a service becomes much more economical. Our calculations show that you can have, it will be 50% of today's cab driving costs. So you'll pay half of the price that you pay today for a taxi if you wouldn't have the driver in the loop. So it means that in cities, it will be much more economical not to own a car, but call a autonomous car and go to wherever you need to go. And these cars would go 24/7.
So why are the car companies being excited about this? There's going to be fewer cars bought.
So the reaction of the car industry. So the reaction of the car industry is you see that there could be a disruption coming into the future, and if you ignore it, then you'll be disrupted. So rather than ignoring it, you come and say, okay, if I'm part of this disruption, I can find new business models. So rather than just producing cars, I'll be part of the mobility business, not only the production.
And you see GM being that nimble and doing that?
No, they bought a company called Cruise Automation, and they're very serious in building autonomous cars, and they're very open about their end game. Their end game is to be a mobility company, not just a car producer. And other car companies are playing. Ford, for example, is doing the same thing. They created a company called Argos AI, which is also building autonomous cars. They're asking for outside investments into those units, both GM and also Ford. So the car industry is understanding that there could be a disruption, and are becoming an active participant in this emerging technology in order not to be disrupted.
Are there any public companies, not the obvious ones that are working on it, maybe in some of the cyber or the lasers, other areas that you have observed are doing phenomenal things that are, for example, a division of a public company that's working on something that you've been impressed by?
Well, there are many companies that are working on pieces of the problem. Like companies that are developing laser scanners, the solid state laser scanner. There are several, I'd say more than 10 known companies, and I imagine there are many more that are still in the embryonic stage that we don't know about, just building sensors. There are companies that are involved just on the mapping side. So there are companies working on pieces. The number of companies working on the end-to-end solution, like we are, is very, very small. Which is Waymo. Apple, we don't know what they're doing, but let's assume Apple. There's Waymo, and then GM and Ford with their companies. So the number of players is quite small because the problem is very difficult and it's multidisciplinary. It is you need to solve many problems together.
I guess what I'm trying to understand is, so let's say in the next 3 years where you're sort of in this embryo stage, are there any public companies, whether they be cyber, which area is going to actually profit from this, over the next 3 years, are there any public companies that actually could profit from this? Not necessarily what you're doing, but maybe people are providing cybersecurity or any areas.
Not the profit won't have an industry. Right now we're under the development stage. So nobody is profiting. Everybody's just investing. Once there is a deployment, then you start talking about profit. So for example, 3 weeks ago, we made a public announcement that we and Volkswagen Group, not just the Volkswagen brand, created a joint venture in which in 2022 we'll commercialize mobility as a service with autonomous cars, with VW cars and our technology in Tel Aviv. And that will be the first city, and then they'll be scaling up to all the cities. So here it is, and with a business plan to profit. So until 2022 we invest, and from 2022 we start building a return on investment that will eventually, ultimately lead to a profitable business.
So for us as investors, I guess this is just
You'll be gone.
educational.
No,
Yeah,
you won't be
we should
here.
be looking at pot stock now, I guess.
You should be here, you won't be, correct.
No, it depends.
Your kids may benefit from
No,
that.
when you think about investments, there's also long-term investment.
No, for you guys, but I guess what I meant more, and I'll let someone else have, is that sometimes, for example, when there was a gold rush, the people in money sold the gold pans, and I was curious whether there are any companies, for example, there might be a pure play cybersecurity company that we're not aware of that actually has a solution which they'll be in the forefront, providing people like you and other companies working on these solutions, and they'll be making money even though you guys are still in the R&D stage. I mean, it doesn't sound like that's the case, but that was my question.
Okay, so Seth gets the last question, and then I get the ultimate. He gets the penultimate, and I get the ultimate.
This is a reasonably new field. What did you do before this, and what about autonomous cars do you find so compelling to devote your career to?
But I'll start with the last question. Why is it so compelling? As I said, this is the ultimate platform for developing AI. And AI is really the stuff of the future. If you think about what has changed in the past 10 years, there are big problems to solve. Curing cancer, energy problems. Those problems still exist. What has changed really is the impact of computing. Computing has made huge strides in the past 10, 20 years, and it's affecting our life. It's affecting starting from the PCs, the social networks, the internet of things now, the rule of algorithms. And in the future, and that future is not far away from where we are today, now computing will start taking cognitive tasks that we humans do and automate them. So, and this is all around artificial intelligence. So artificial intelligence, AI, is the future. And if you don't have a good handle on AI, you will not exist in the future. This is why it's very, very compelling to research and develop in this area and innovate in this area, because it's going to determine the future. And autonomous cars is the ideal platform for developing AI. I do other things which I didn't have time to talk about. I have another company that is developing AI for wearable computing, starting with the blind and visually impaired. And we are also moving to broader segments of society, not only the blind and visually impaired. Treating AI as a companion, treating computing as a companion, as if you have another sensor and another brain on you all the time, and what kind of value it can provide. Besides that, my area of research is machine learning, computer vision, artificial intelligence, quantum computing. We do a lot of relationship between machine learning and quantum mechanics. They are very close. They can feed each other. There are all sorts of problems in quantum mechanics of simulating systems that if you understand machine learning, you can simulate them much more efficiently. And there are things that physicists have solved that could help practitioners in machine learning. So building the bridge between machine learning and quantum mechanics is an area that I'm very interested in, and I'm very active there. So this is my life.
Okay, so I get the last question. And since this is a Hebrew University event, I feel compelled to ask you this, which is, how did Hebrew University contribute to your success? And given that your company has been so successful, why are you still an active professor at Hebrew University?
Well, money is the secondary thing. What makes me wake up in the morning is making an impact. So the fact that I had a very nice exit with Mobileye being sold to Intel, or when Mobileye became a public company, that is a momentarily, it's a very transient achievement. Okay, so what do you do the next day? The next day you want to continue working and creating an impact. And this is why I continue in academic life, because in my business life, you end up managing, a lot of people. And so, for example, Mobileye has 1,500 employees. At Intel, I have few hundreds in addition. Orcam has about 250 employees. So when there are so many people, you cannot get into the fine details all the time. In my academic life, I work with a small number of students. I have 2 PhD students, 2 master students at any given time. And you need to work on the details, right? You cannot just look at things from a high level. You need to solve a problem from beginning to end with all the details, so it keeps your mind sharp. Right? If you're only managing, you become more and more and more stupid. Right? You have to work really on the details. And this is what the academic life gives me. This is why it was very important for me to keep on the academic life, even though it's difficult. It's very, very easy to let go of things and just enjoy life. So this is why I maintain this.
Thank you very, very much. Really appreciate your taking the time to to come down and educate us. And I know that all of us will take away, a much better understanding of the technology that's going into the driverless cars, which are going to affect all of our lives. But I think there's one other takeaway that I hope people will have tonight, and that is that a lot of there are discoveries and technological breakthroughs, some bigger than others, that are being made every day at Hebrew University. And when our family decided to get involved with Hebrew University many, many years ago, we had no idea where it would take us. We knew that we wanted to be involved and support education in Israel and to support the state of Israel, but we had no idea where our journey would end up. And obviously, we are very proud of our success. But I hope that those that are here tonight, some of you that don't have that much involvement previously with Hebrew University, I hope that perhaps you'll be motivated to begin your own journey with our family and to see where that might end up. And I know that based on our experience, you won't be disappointed.